Hello and welcome to today's video. So on the workbench today we have the Nissan Leaf BMS. This is the one with my microcontroller in there running my code. And the whole point is to emulate everything that they're doing, that Nissan's doing in their BMS with mine, so then we can modify that to be able to work with less modules and less cells like I'm doing for my truck, the battery packs that I'm building for my truck. So anyways, if you recall from a previous video, everything's still set up. We're doing the temperature sensors here. They're in this environmentally controlled system known as a box. And yeah, it's just to keep any kind of stray air currents from cooling off the system and affecting any readings. But anyways, we got that in there and it's all hooked up. And oh yeah, I forgot. So in one of the previous videos I was mentioning that I need a way to test pack sniffers. So here's a brand new pack sniffer that I haven't actually screwed into the box yet. But in order to test them, I'm not going to have battery pack anymore because I'm going to take mine apart. And so people are suggesting, well, you can just use the BMS unit. Well, I'm planning on using my BMS units. I won't have like a spare floating around specifically to test battery packs. And thus, the pack simulator was born. So this is using one of my little servo controllers here. And I got everything populated to make that run, and then the LEDs just simulate the contactors. So the small green one, yeah, I didn't have like another color, so the small green one is the ignition switch, and then the other ones represent yellow is the pre-charge, and green is the negative contactor, and the red is the positive contactor. So yeah, this is my, so once I'm done with the code for this, then I'll just clone that over to this microcontroller and then it'll spit out CAN packets as if it is the real Nissan Leaf battery pack, and I'll put some fake cell values in there and fake, you know, temperature values and everything, just to make it show up on here and to know that everything's working and is reading. I mean, in reality, if it can see a CAN message, then, you know, CAN bus is running, and if it can turn on the LEDs, then, you know, that's working. So if you're just there to test, you know, the hardware, but people may not like that, and they just want to see it actually say some, you know, report some cells on there and everything. So it'll do that. So that's what that is. And then, of course, we have the other pack sniffer. This is my development one that's, you know, heavily modified and has all kinds of extra stuff on there to control extra things, and it's the prototype for pack sniffer version 2. This is a version 1. But anyways, we'll get back to, if you recall in the previous video, this guy, every time there was a temperature change, it spit out a CAN packet, and I have all that data on the laptop here, so come over here. So on the laptop, you will see these are all the bytes that were received from my from the Cavasar using their CAN Kingdom program to record all of that, and then I've went through Excel here and converted all the bytes back into actual A to D values here. And then this column is the average of the 3 temp sensors, because there's actually a lot of variation in them. They're not super accurate, and yeah, I'm not that impressed with the temperature sensors they're using. They aren't very, very accurate, but you know, they're getting in the ballpark. That's probably all they really care about. So all of this other stuff is the actual voltage that was on the A to D, and everything gets calculated out. And if we scroll over, so you know, there's like pages and pages and pages and pages of data, and I just dumped it all in here for let Excel do all the processing for me, right? So if we go back to the top, and if we scroll over, we get this nice little graph. You can see there's a few different colored lines there. I don't know how well they show up. There's a red, green, and blue temperature probes, each of the temperature probes, and then an average value, which is the one on top, which is this orange line. And you can kind of see, yeah, if the dots are smaller, you kind of see how they're all, you know, they all kind of intersect around 25 degrees is where they all kind of join up, and then they kind of diverge a bit. And that appears to be pretty common. if we go over to the manual for the Nissan Leaf, that actually tells you here's the temperature sensor characteristics, and they show a little graph here, and at 25 degrees Celsius we know that the temperature sensor should be 4 kiloohms, and they're really close to that. I tested them at 25 degrees. They're really close. They're about like 3.85 or 3.95, I don't remember, kiloohms. 25. So they vary. There's a little bit of variance depending on which one you measure. So I kind of just took the average of them, and then I built this table here, which is the opposite, using the average data. So essentially we have an A to D converter value in and temperature out. And the problem is that I went up to 100 degrees Celsius on this side, but on the other side I could only get to about 18. You can see it kind of acts funny down here, so I don't trust the data at this end. Actually, I don't trust this part, because I think it's actually, I think because I just put it in the freezer, I think my temperature is dropping faster than my the probes could keep up. They have a pretty long time constant. Anyways, I generated this, I don't know if you can tell, but on top of this line there's a 6th order polynomial trend line that I've put on there. With a r-squared value of 0.9999, so it's really close. 1 is perfect. So this represents that curve, and took all of that data and developed, using this equation, developed this handy table over here, where now I can type in essentially I just need 3 temperature points. So we know at 25 degrees Celsius, I measured my temperature probe to be 38 or 3.85 K, and at minus 15 degrees, I measured it to be 22.339 K, and at 95 degrees, I measured it to be 444.5 ohms. So if you put that data in there, it auto-calculates all of this stuff for you. We know that the BMS uses a 4.7K resistor divider with that in series. The variable, or the thermistor, is the bottom leg to ground, and then we have 5 volts coming in on the top. And by putting all that data in, it generates a ROM table for you. That is starting off. I mean, you'll never get up to these, like, if the A to D converter is reading 2, you're at 588 degrees Celsius, which, yeah, you're never gonna be there. But maybe I scroll down to somewhere reasonable temperature range here in the 20s. So if you look here, you're at 25 degrees. 25.5 degrees is 3,778 ohms, and yeah, that gives you this value, which is 25.49 C. So that's what the ROM table is in this format. So there's a decimal point right there, right? So it's 25.49. So if we read 2066 on the A to D converter value, then we are at 19.39 degrees Celsius. So pretty simple. So I've built the entire table. It goes to crazy values all the way to 4095, which is the highest voltage. It's 5 volts on the A to D converter, and of course we can't actually get there, so I put out, the highest voltage we should be able to read if you 4094 counts is actually negative 102 degrees, negative 102.82 degrees Celsius. So yeah, we're only going to be operating this, but I built the whole ROM table. Each one takes up 2 bytes. Assigned value, and yeah, so this recalculates live, so I can go and measure my resistor here and say we measured that this one was 30K. You type that in, you can see it just recalculated the entire table for you, the ROM table. So I haven't decided yet if I'm just going to do a generic one. This is what I've kind of got in there. I took the averages of everything and generated this generic table, and these are all the average values, so it's close. It's not going to be perfect because it's actually pretty close on one of the sensors. The other 2 are kind of outliers, but it's gonna get the job done for for what I'm looking for. But anyways, I took this ROM table, and if we flip over the code, yeah, here it is right here. So I just dumped the ROM table. It's this giant, long, huge thing here. But yeah, really simple. We just use the A to D value as essentially the index into the table, and then it just returns the value. Yeah, you can see here it literally just returns the index, the value it finds in the table. And then this is stored in program memory. I'm debating about having one individual for each temperature sensor. That might be a bit overkill, even though with this huge table in there of 4096 words, I'm still only using up 8% of my program space in my micro, and that's it, with it doing pretty much most everything. So yeah, I got plenty of room, so I could do it. I could actually just, I've got almost 15.3K free. You could almost have it in RAM, but you know, it's a lookup table. I might as well put it in Flash. Flash on these micros are very quick. Anyways, yeah, let's see this puppy in action here. So go ahead and turn on power. And there you go. So this is the I2C temperature, which is 21.93. And then you can see that I'm reporting back that it's 22.01 or 22.16 or 22.04. So they're all pretty close. And yeah, I mean, it seems to be working pretty good. So yeah, this video is kind of long, but I guess we could run some current through the sensor here. We'll just go ahead and click that on, and we'll run what do you want to run? Let's put an amp through it. Should warm it up pretty quick, right? It's a 10 ohm resistor. And you can see everybody going up. See, they track rather well. But I'm quite happy with the performance. I think I like it. Ooh, now we're really heating up. And I think what's happening is these probes are faster than the I2C temperature sensor. Or at least I have higher resolution on mine. Anyways, yeah, looks pretty good. Go ahead and see, this guy is lagging behind. Well, it could be where they're positioned too, so what I should do is actually, you know, back off on the current, let it actually stabilize, and then they'll probably all be pretty accurate. Because I think the one on the end here is actually, if you look inside the box, I think it's the one on the edge that's not quite. Yeah, I don't think he's actually in all the way. But they're kind of hanging off of there. The ones on the end seem to be pushed against the heatsink better than than sensor number 1 there, which is the one that seems to be lagging behind. But anyways, yeah, it looks like it's working. Anyways, thanks for watching. Bye.